So good morning guys. In this video I'm going to be teaching you and I'm going to be solving possible page 103 questions. Possible questions on page 103, like the short ones, because it says questions on the slide. So let's know how to solve questions from the side. So the reason I'm not showing my face in this video is because of the marker board and the classroom I use is not available, so I just have to shoot like this and let's get the video started. So the question is going to be projected on the screen. Don't worry about it. You don't have to go through the video description to download the question. It's going to be projected on the screen right here, as you can see it right now. So it said a constant volume gas thermometer records a pressure of 240 millimeter mercury at lower fixed point. You know, when you are comparing temperature to thermometric properties, you just have to draw two lines like this. So they said it records a pressure of 240 millimeter mercury at the lower fixed point, and lower fixed point is what, 0 degrees Celsius. So that's 0 degrees Celsius here. At lower fixed point of pure water, and 300 millimeter mercury at upper fixed point of the same water. And when it's 100 degrees Celsius, 300 millimeter mercury. And I said calculate the room temperature when the gas pressure is 280. 280 when this one is 280 millimeter mercury. What is the room pressure? Let's call the room pressure X. So we're looking for X. So to solve questions like this, you just need to compare the stuff, and anything you do in this place, you do also in this place. So let's say that's 280 minus 240. Now the pressure minus the lower fixed point, upper fixed point minus lower fixed point, and we also do the same thing here. So 280 minus 240 over 300 minus 240. 300 minus 240. Here we say x minus 0, which is also x, over 100 minus 0 is 100. So 280 minus 240 is 40 over 300 minus 240 is 60 here. Is equal to x over 100. Then we can this can cancel this, right? Then we can say x is equal to 4. This cancel 2 here, 2 here, 3. Understand? So we can say x is equal to 200. When we multiply 100, we cross multiply. So 100 times is 200, 200 over 3. So the room temperature is, let me use my calculator. Room temperature will now be 200 divided by 3, and that is 66.67 degrees Celsius. 66.67 degrees Celsius. So that was question number 1, and that's how to solve it. So another kind of question like that, they said, as you can see, it projected on the screen. So they said if the electrical resistance of a platinum at 0 degrees Celsius, so when it's 0 degrees Celsius, is 10.5 ohms, so that's 10.5 ohms, and 12.8 ohms at 100 degrees Celsius, and 12.8 ohms when it's 100 degrees Celsius. And I said calculate the temperature because when the resistance is 11.75 ohms. So just like the last question we did. What you should know about this is one of the is that they repeat questions from the slides. So that's why I'm solving this, so you'll be familiar with questions like this. We've not gotten to the real deal, this is just the easy part. So here with me. X minus 0 is x over 100 minus 0 is 100. Then do the same thing here. 11.75 minus 10.5 all over 12.8 minus 10.5. I think I prefer videoing like this because to stand and teach is quite difficult. Quite is difficult. It's stressful. So I think to teaching like this is actually better. Okay, so 11.75 minus 10.5 will give you 5 over, that's 1.25, 1.25 over 12.8, 12.8 minus 10.5 will now give 2.3, 2.3. So when we cross multiply, the value of x will be 1.25 times 100 divided by 2.3, and that will give me 54.35 degrees Celsius. So that's how to solve question number 2. I think I enjoy videoing like this, but I want to advance to using pad, like maybe a tablet and a stylus pen to teach, because it's going to be way easier than that, and I can just teach anywhere I am. So that's how to solve questions like this. X is equal to 54.35 degrees Celsius. Next question. Next question will be projected, as you can see right here. They said find the difference of two temperatures, 40 degrees Celsius and 90 degrees Celsius in Fahrenheit. So before I solve this question, let's just recap on what we know. We should know that the difference in temperature in degrees Celsius is equal to different temperature on the Kelvin scale. they are equal. So 50 minus 40 degrees Celsius is also 50 minus 40 degrees Celsius is 50 minus 40 degrees Celsius will give you 10 degrees Celsius. It's also 10 Kelvin. The difference is equal, but the value is not equal because we know that TK is equal to TC plus 273. That's when we are converting, right? But the difference on the scale is equal to the difference of the scale of the Celsius difference is equal to difference of the scale of the Kelvin. Why? Because they have the same fundamental interval. Understand? You know what the meaning of fundamental intervals? The difference between the upper fixed point and lower fixed point. That's all. So, and you should also know that the difference in temperature of Fahrenheit is equal to 9 over 5 the difference in temperature of Kelvin. So, you should know this. But you know, if you are converting from Fahrenheit, you're converting Kelvin to Fahrenheit. Sorry, Celsius. This is Celsius. And it's also Kelvin also. You can also say, you can also put Kelvin, also put Celsius, anyone you want. So the degree of Fahrenheit is also, to convert is 9 over 5 TC plus 32 degrees. Sorry, plus 32. So these have to come out from Celsius to Fahrenheit. I'm not to do from Fahrenheit to Celsius, you just make your subject formula and change your subject formula and you find it. So let's go into the question we have to solve here. So they said find the difference of two temperatures, 40 degrees Celsius and 90 degrees Celsius in Fahrenheit. So the first temperature is 40 degrees Celsius, the second temperature is 90 degrees Celsius. But we are looking for the difference in Fahrenheit. So what is the difference in Celsius? The difference in Celsius, or change in Celsius, is equal to 90 minus 40. 90 minus 40, which is 50 degrees Celsius. So what is the difference in Fahrenheit? The slowest way and the let me say the very slow way, like very very slow and not so wise way, is to convert the Celsius to Fahrenheit, then make the difference. You're going to waste a lot of time. So change in CF is going to be 9 over 5, change 9 over 5 change in TC. Understand? So the difference in Fahrenheit will now be 9 over 5 times 50. Change in TC is 50. So 5 here, 5 in 50 is 10. That's 50 divided by 5 is 10. And 10 times 9 is just 90. So that's 90 degree Fahrenheit. You have to solve questions like that. So there's also some questions I'm going to be projecting it at the side of the screen. They said find the equivalent of the following on the Celsius. So they gave us Kelvin. That's question number one. They gave us Kelvin to be 305 Kelvin. And they said what is it in the Celsius scale? You should know TK is equal to TC plus 273.15. The 15 there is important in this part of physics. So NTK is 305. They're asking us to find the Celsius. So what are we going to do? Just you subtract 273.5 from both sides of the equation and that'll be 305 minus 273.15. When you subtract 273.15, it cancels out. So don't bother writing it. So 305 305 minus 273.15 will give 31.85 degrees Celsius. And that's the answer. So that's 1A. Then 1B, I'm coming. So 1B, they said they gave us Fahrenheit to be 215 Fahrenheit. I said I should find what? Okay, the value in Celsius. So what do? We all know the formula TF is equal to 9 over 5 TC plus 32. And what is TC? TF is going to be 215 9 over 5 TC plus 32. You subtract 32 from both sides of the equation and that'll be 215 minus 32. 215 minus 32. That'll be 183. 183 is equal to 9 over 5 TC. Then what's your TC? Just multiply 183 times 5 and divided by 9 and you get 101.67 101.67 degrees Celsius. So question number 2, they said a pan of water is heated from 70 degree Fahrenheit to 175 degree Fahrenheit. You should do that yourself because I've done an example on that. So just use my example and you do it. Number 3 said if the difference between two temperatures, everything is just same. Everything is just same. All you need to know is just change in TK is equal to change in TC and change in TF is equal to 9 over 5 change in TC. If you know this, then you can solve temperature difference very fast. So we are moving with the speed of light because our exam is on Monday and you need to do very well in the exams. Move to the next question. Yes, this question they said a constant volume gas thermometer is calibrated in dry ice, right? No, dry ice is CO2. That's I think solid carbon dioxide. In the solid state, okay. which has a temperature of minus 80 degrees Celsius. So since they calibrated it in dry ice, that means the lower fixed point is minus 80 degrees Celsius. And in boiling ethyl alcohol, 70 degrees Celsius, that's the upper fixed point, 70 degrees Celsius. The two pressures, that means when they calibrated it, the pressure at lower fixed point was the two pressures are 0.9 atmosphere and 1.635 atmosphere. 1.635 atmosphere. So they asked determine the fundamental interval of the scale. You should know fundamental interval is just up, upper fixed point minus lower fixed point. So question number 1A, upper fixed point here is 78 minus negative 80 degrees Celsius. So that's our fundamental interval. And if you use your calculator, 78 minus 80 is 158. So that's the fundamental interval, 158. You don't need to put anything, it's just 158. So B said determine the fundamental intervals. Okay, A. B said what Celsius of absolute zero does the calibration use? So what I'm trying to say is what Celsius of absolute zero? Absolute zero here is minus 273 minus 273.15. Okay, you should know our normal absolute zero is minus 273.15 degrees Celsius, right? But they're asking us what Celsius value is absolute zero. That means they're asking us the absolute zero of this particular this particular temperature. Normally our absolute zero is minus 273.15, but in this thermometer it is different. So they're asking us what is the absolute zero on this thermometer. And at absolute zero, our atmosphere is our pressure. Sorry, our pressure is always zero atmosphere. Zero atmosphere, zero everything, 0 millimeter mercury. Everything is zero. Pressure is zero at absolute zero. Why it is negative below absolute zero, but at absolute zero, pressure is zero, and absolute zero is 0 Kelvin or minus 603.15 degrees Celsius. So they're asking what's the value of absolute zero. So let's just call that x, and we just do our trick. Any subtraction we make here or anything we do here, we also do in this place. So let's say b minus 80 minus x all over 78 minus x. So we also do it here. That is 0.9 minus 0.9 minus 0 over 1.635 minus 0. So this will be minus 80 minus x. Okay, let's be fast about this. Let's just cross multiply. That will be 1.635 minus 80 minus x equals to 0.978 minus x. So let's open the bracket. I have 1.635 times 80. I have minus 130.8 minus 1.635x. And 0.9 times 78, 0.9 times 78 will give 70.2 minus 0.9x. And we just collect the like terms. So that will be yes, 1 minus 133.8. When we subtract minus 70.2 from both sides, that will be minus 130.8 minus 70.2 is equal to minus 0.9x plus 1.635x. So minus 130.8 minus 70.2 will give me minus 201. Then minus 0.9 plus 1.635 will give 0.735x. Then we divide both sides by 0.735, and what we get here is 1 divided by 0.735. What we get here is minus 273.47 degrees Celsius. So that's the absolute zero temperature on this thermometer scale. So question C. Can you see the screen? Let me bring it forward a little bit so you can see it. That's what I'm solving. So C says, yeah. So C says, what is the pressure at the freezing point? What is the pressure at the freezing point? So let's go back to the scale. He said, what is the pressure at the freezing point? At the freezing point of water. The freezing point of water is 0 degrees Celsius, right? So this is where 0 degrees Celsius will be. 0 degrees Celsius, because below zero will be negative. So they're asking us what is the pressure. What is the pressure here? So how do we solve it? How do we solve it? How do we solve it? I think I'm going to redraw the scale to how else we moving the camera. So what is the freezing point of water? So let's call this y because we used x. So let's just call this y. So we can just say 0 minus 80 over 78 minus minus 80. No, we are just saying 0 minus this temperature over 78 minus this temperature is equal to, I also do it here as y minus 0.9 over 1.635 minus 0.9. So we can just say this is 0 plus 80. So we can just call this 80 over, and we can call this 158 is equal to y minus 0.9 over 1.635 minus 0.9 will give 0.735, 0.735, right? So to make y the subject of the formula, I just say y minus 0.9 is equal to, let's just solve this, as 80 times 0.735 divided by 158, and that was 0.372, 0.370, 0.372. Then y just have to add it as 0.372 or 0.9, and that will give 1.272 atmosphere. So that's the answer. So at the freezing point of water, it is, the pressure is 1.27 atmosphere. So question D now says, what is the pressure at? Let's draw the scale. So this is the scale. Let's draw the scale. So we have to move in the camera. The camera 1.635, 0.9, right? 78 minus 80. Okay, so they asked what is the pressure at boiling point of water. Boiling point of water is about 100 degrees Celsius. So we just have to take this up a little bit, 100 degrees Celsius, because 100 is above 78. So the pressure here is also going to increase. So let's call that Z. So how do we do this? If you can do this, pause the video and solve. Let's get right back. So let's just say 78 minus 80 over 100 minus 80 is equal to 1.635 minus 0.9 over Z minus 0.9. So here, what's 78? That's 70. This is what eventually turns to 78 plus 80. So that'll be 158. That'll be 158 over 180, right? Is equal to 1.635 minus 0.9 will be 0.735, 0.735, all divided by Z minus 0.9. Oh, I'm not seeing it. Let's bring it down a little bit. Z minus 0.9. Yeah, that's what I did. 78 minus 180. This gives 450. This gives 180. Okay, so what do? We just, let's cross multiply. We have here to be 158 Z minus 0.9 equals to, then when you multiply 180 times 0.735, 180. Cross multiply 180 times 0.735, we give 132.3. So instead of opening this bracket, we can just divide both sides by 132.3. You can divide both sides by 158, and that will be 132.3. 132.3 divided by 158. That will give me 0.837. 0.837. Then we can just add 0.9 to both sides, and that will give, what should I give? 0.837 plus 0.9. That will give 1.74 atmosphere. So that's how to solve question like that in case it comes out. Okay, yeah, this one will likely come out. Of course, this kind of question is likely going to come out. They are going to see it on the screen. A segment of steel railroad track has a length, that is the initial length, the original length is 30 meters, right? Let me take this inside so you don't. Yeah, it's 30 meters. when the temperature is 0 degrees Celsius, that means when the initial temperature is 0 degrees Celsius. What is the length? What is the length in the increased length L2? Let's call that L2. When the temperature is 40 degrees Celsius, and temperature is 40 degrees Celsius. So then the coefficient of linear expansion, of course, it has to be given of steel is 11 times 10 raised to the power minus 6 degrees Celsius. The question A says what is its length at 40 degrees Celsius? So we all know that you should know this formula. L2 coefficient of expansion is L2 minus L1 or L1 change in T. We are going to apply this formula in this question. 11 times 10 raised to the power minus 6 is equal to L2 minus 30 over 30, that's our L1. And our change in temperature will be 40 minus 0, that will be 40. The change in temperature is just the final temperature minus initial temperature. That's going to give 11 times 10 raised to the power minus 6 equal to L2 minus 30 over 30 minus 40 is 1200. So you can see L2 minus 30. Let's cross multiply. That's 11 times 10 raised to the power minus 6 is 1200. That's 0.0132. Right, 0.0132. Then L2, you just have to add you just have to add 30 to both sides. You know, when you add 30 to here and you add 30 to this place, this cancels out. So you just have to add 30 to both sides. And L2 will be 0.0132 plus 30. And that will give 30.0132 meters. So that was the that's how to solve question. That's the answer for question A. 1A. So B says suppose the ends of the rail are rigidly clamped at 0 degrees Celsius so that expansion is prevented. What is the thermal stress set up in the rail if its temperature is raised to 40 degrees Celsius? Take the Young modulus of the steel. So Young modulus of the steel is Young modulus stress over strain. For those that don't know, so Young modulus is 20 times 10 raised to the power 10 Newton per meter square. That's the value they gave us, and the coefficient of linear expansion is already given here. So what are they asking us to find? Said what is the thermal stress? The thermal stress, not stress. So Young modulus is stress over strain, right? And we are looking for stress, but what's strain? Strain is extension over length. And it's the extension of the extension or the expansion, extended length divided by the original length. Right. So what's our Young modulus? Our Young modulus is 20 times 10 to the power 10 is equal to stress. We're looking for stress. What was our strain? We don't know yet. So since strain is extension over length or expansion over length, extended length over length. Our extended length, it will be L2 minus L1. That's our change in length, right? So that will be 30.0132 minus 30. That's the final length minus the initial length. So divided by the original length, that's the initial length, 30. So that will be 0.0132 divided by 30. And that will give us 0.0132 divided by 30. That will be 4.4 times 10 to the power 4. So strain, should I write? Let me write it here. So strain will be 4.4 times 10 raised to power minus 4. That's 4.4 times 10 raised to power minus 4. Then, since we've gotten strain, then our stress, we just have to multiply Young modulus times the strain. And that will give, you have to multiply the Young modulus times the strain. That will give 20 times 10 raised to power 10 times 4.4 times 10 raised to power minus 4. That will give 8.8 times 10 raised to power 7 Newton per meter square. So this is the unit of strength. 8.8 times 10 power 7 Newton per meter square. Because stress is, this is the unit of stress. Because stress is what? Stress is force over area. But strain does not have units. So let's go to the next question on this same page. That's question 2. So question 2, let's go. Question 2 says the active element of a certain laser in a glass rod 30 centimeter. The active element of a certain laser is a glass rod which is 30 centimeter long by 1.5 centimeter in diameter. So the diameter is 1.5 centimeter. If the temperature of the rod increases by, that's the change in temperature, increase by 65 degrees Celsius, because it increases by, means if you hear something like increases by, that means if you are hearing something like increases by, yeah. So if you hear something like increases by, that means you already have a difference in temperature. But if you hear increase to, you still have to like find the difference. But increase by, very just simple prepositions. So if the temperature of the rod increases by 65 degrees Celsius, what is the increase in its length? So they're asking us for the increase in length, increase in diameter, and increase in volume. So I'm just going to do the one for increase in length and tell you how to do the one for increase in diameter and increase in volume. Let's find the one for increase in length. They said assume the linear expansion is 9.0 times 10 to the power minus 6 per degree Celsius. So you should know linear expansion is equal to change in length all over the change in length, you know, is L2 minus L1, still change in length. Original length times change in temperature. This is 9 times 10 to the minus 6. Our correction to linear expansion. Change in length is what we're looking for. The original length is 30 and the change in temperature is 65. So when we cross multiply, change in length is just going to be 9 times 10 raised to power minus 6. 9 times 10 to the power minus 6 times 30 and 65. And that will give 0.0176 meters. So to find the one for diameter, you're just going to use, to find the one for the change in diameter, you use exactly this format. It's just that don't go ahead to look for the area, maybe since it's a rod, you look for the area of cylinder, then you're going to waste your time. You treat the diameter like the way you treat length, and you just get the same answer. So this change in length will be the change in diameter, this length will be your original diameter, then you just look for it. I have more questions to solve, so I don't want to waste time solving it. Why to look for volume, to look for change in volume. That's when you do the volume of the cylinder. And this linear expansion just multiply times 3 because it's now a cubic, the cubic expansivity. Not it's not be linear expansivity, it's now a cubic expansivity. So you have 3 times linear expansivity. And you know, superficial, the area expansivity is 2 times the linear expansivity. You should also know this. Let's look at the next question. Okay, so the next question, you're going to see it on the screen. You can see like a circuit, like two electronic devices. One is silver, while one is given brass color. So the information about all the steel and the space, everything is given. So we're going to use this diagram to solve the questions. So they said a poorly designed electronic device has two bolts attached to different parts of the device that almost touch each other in its interior as shown in the figure. The steel and brass bolts are at different electric potentials, and if they touch, a short circuit will develop, damaging the device. The initial gap between the ends of the bolts is 5 micrometer at 27 degrees Celsius. At what temperature will the bolts touch? Say correlation to linear expansion for steel and brass respectively to be 11 times 10 to the minus 6 per degree Celsius and 19 times 10 to the minus 6 per degree Celsius. So what are you asking us for? They're asking us at what temperature will these these two these two electron device will they expand and touch each other, then the circuit blows. Because when they touch each other, the circuit blows. So We are looking for the temperature at which they are going to expand. So if you look at the diagram now, the space in between the two, as you can see, the space in between the two materials, that's steel, the steel and brass, is 5 micrometer. So for for us to find the temperature is going to expand, you should know that when the space as they expand, the length at which brass will expand and the length at which steel will expand is what is going to occupy that space. So we can say the space now, the space that's like 5 micrometer, that space there is going to be is going to when the expansion of the expansion of the steel, that's when the steel expands, the expansion of the steel plus the expansion of the brass. It's just like we have two bodies here. We have two bodies here, and this space here is 5 meter, right? And two boys want to push this body. Let's say they push this body simultaneously. So as they push this body simultaneously, this body jams together. So you know that the distance here, the distance between the two bodies, the initial distance between the two bodies, when they come together, is going to be the distance of this body moved by the distance of the body moved because the both body occupy that space. So it's just the same thing as this place. The space is the expansion of the steel plus the expansion of the brass. So if we can get that, it will be very easy for us to solve it. So you should just know that the space here is 5 times 10 to the power minus 6 meter. That's 5 times 10 to the power minus 6. That's 5 micrometer. The expansion of the steel, that's change in length of the steel, plus the expansion of the brass, that's change in length of the brass. So this is what we are going to use to solve and get the question. So let's look for the expansion of steel. That's change length of steel. So change in length of steel will be linear expansivity of steel times the original length of steel times the change in temperature. So for steel, the correction to linear expansion is 11 times 10 to the power minus 6 times the initial meter is 0.01 from the diagram, and the change in temperature, we do know that. So that, let's say that will be theta minus 27 degrees Celsius, right? So let's just multiply this together. Let's just multiply this together. 11 times 10 raised to the power minus 6 times 0.01. That was 1.1 times 10 to the power minus 7 bracket theta minus 27 degrees Celsius. Why for brass? We don't know this theta because that's what we're looking for. So let's just continue. Theta, the change expansion for brass will be linear expansion of brass times the original length of brass times change in temperature. So for brass, the linear expansivity is 19 times 10 raised to the power minus 6. The length is 0.03, and change in temperature is just theta minus 27 degrees. This is at same temperature difference, same temperature. All of them are under one temperature times 0.03. So this here gives 5.7 times 10 raised to the power minus 7 theta minus 27 degrees Celsius. So let's plug these two values we've got here. Let's plug it into this equation here. So that will be 5 times 10 raised to the power minus 6 meter is equal to, this will be 1.1 times 10 raised to the power minus 7 theta minus 27 plus 5.7 times 10 raised to the power minus 7 theta minus 27. So what can we do here? We can say 5 times 10. So let me position it. So we can say 5 times 10 raised to the power minus 6 meter is equal to, so we can just factor out uh, theta minus 27 degrees Celsius, right? We can factor out theta minus 27 degrees Celsius from the whole of this equation. We can factor out theta minus 27 degrees Celsius, and we left with 1.1 times 10 raised to power minus 7 plus 5.7 times 10 raised to power minus 7. Right? So that'll be 5 times 10 raised to power minus 6 meter. 6 meter with theta minus 20, theta minus 27. Then let's add this together. That will be 1.1 plus 5.7. That will be 6.8 times 10 raised to power minus 7. So you have to just divide both sides by 6.8 times 10 to the power minus 7. 6.8 times 10 raised to power minus 7. Just cancel this. And we're left with here to theta minus 27. Then 5 times 10 raised to power minus 6. 5 times 10 raised to power minus 6 divided by 6.8 times 10 raised to power minus 7. That gives 7.35. That gives 7.4 degrees Celsius. So what's our theta? Just have to add 27 to both sides of the equation and this cancel this. So theta will be 27, 27 plus 7.4 degrees Celsius. That's 27 plus 7.4 degrees Celsius. That's 34.4 degrees Celsius. So our answer is 34.4 degrees Celsius. So this is a better way of solving this question because the way they solved it in the slide, you are going to get one temperature like that. Okay, you first get the 7.4. Then a lot of people forget that they have to add it. They have to add the temperature with 27. Then they miss it. But when you follow the format I used, you will know that okay, what you are looking for is theta. So if I get theta, I've gotten my answer. Understand? So the best way is to understand how to solve it, not just cramming the way you solve it in the slide, because it will probably come out in this exam. Question: when the temperature of an aluminum rod was increased by the change in temperature was increased by x degrees Celsius, the ratio of its original length to the final length, that L1 over L2, is 0.999505. Very long. If the linear expansivity of the rod is 11 times 10 raised to power minus 6 per degree Celsius, then what is x? So what is x? What is x? So you should know. Okay, just go back to the formula. As linear expansivity is change in length over change length L2 minus L1. You should know that over original length times change in temperature. From this expression, you can also say L1 is 0.999505 L2. Understand? So okay, let's go back to this. That's 11 times 10 is power minus 6. Change in length is L2 minus L1, and L2, that's L2 minus L1. What's L1? L1 is 0.999505 L2 over, from this L1 is equal to this, over the original length, which is L1. So that's what's L1. L1 is 0.999505 L2 times the change in temperature which we are looking for. So when we cross multiply, you can say x is L2 minus 0. Okay, let's just do this. L2 minus 0.999 is what? That's 1 minus 0.9995052. 0.0004948 all over L2, sorry, all over 11 times 10 raised to power minus 6 times 0.99995052 L2. So this here will give us a value of x, that's change in temperature. So L2 cancel L2. So when we solve this, what do we get? 0.000948. 0.00. The answer is 45 degrees Celsius. So the change in temperature is 45 degrees Celsius. So there's this question. They said calculate the total amount of energy that must be added to change 1 gram of ice at minus 30 degrees Celsius to 120 degrees Celsius. So this question, if you don't understand a phase change process, you don't understand latent heat and how to calculate, you don't understand when to use specific heat capacity and when to use latent heat, you might get this question twisted. So they said, what is the total amount of energy to raise minus 30 to 20 degrees Celsius? For you to know that, you need to know that this process it occurs in phases. So when you are going to change a temperature of ice to minus 30 degrees Celsius to 120 degrees Celsius, at first, the temperature has to rise from minus 30 to 0. So the quantity of energy used here is mc theta. So this is when it changes from minus 30 degrees Celsius to 0 degrees Celsius. So from ice change to 0 degrees Celsius, like melting ice, changing to water already. Minus 30 degrees Celsius to 0 degrees Celsius. So when it is at 0 degrees Celsius, there's also a change that occurs there, which temperature difference is not detected, and that's latent change. Understand? So that's latent heat. So there is going to experience this phase change. So at the phase change, it will be latent heat of fusion. That's when the ice is melting. That's latent heat of fusion. So this one is at 0 degrees Celsius. So latent heat of fusion. So it's already occurring latent heat of that's latent heat of fusion. So from 0 degrees Celsius, it's going to move from 0 degrees Celsius to 100 degrees Celsius. That's 0 degrees Celsius of water to 100 degrees Celsius of boiling water. So that will be, this here is specific capacity of ice. So this mass times specific capacity of water times the change in temperature. Let's call this change in temperature. Change in temperature. So this one is moving from 0 degrees Celsius to 100 degrees Celsius. You get, that's the third quantity of energy. So when it has moved from 0 degrees Celsius to 100 degrees Celsius, at 100 degrees Celsius, phase change also occurs at 100 degrees Celsius. So phase change occurs at 0 degrees Celsius, it occurs at 100 degrees Celsius. So at 100 degrees Celsius, the latent heat here is latent heat of vaporization, because the water is already vaporizing from liquid to gas. That's this at 100 degrees Celsius. But that's not all. They say it moved from minus 30 to 120. So for it to move from minus 30 to 120, from 100, it has to move to 120. And that is 100 degrees Celsius to 120 degrees Celsius. That'll be mass times the specific capacity of steam and its change in temperature. That's when it moves from 100 degrees Celsius to 120 degrees Celsius. You can see we have five five different processes. So you add all this together and you get your answer. But in the exam, they might not want to set something this long because of time. But they can just ask you how many processes does it undergo to change from minus 30 to 120. So it's your job to do that. So you can ask you different questions on it. So just understand the process and you'll be fine. Okay, so this next question, this one came out in test. So let's solve it. Water flows at the rate of 0.150 kilogram per minute through a tube that's heated by water dissipating 25.2 watts. The inflow temperature 15.2 degrees Celsius, the outflow 7.4 degrees Celsius. When the rate of flow is increased to this and the rate of heating to 37.8 watts, the inflow and outflow temperature remain unchanged. They say find the specific capacity of water and the rate of loss of heat from the tube. So the formula I'm going to use here is the rate of energy supplied by the heater. As rate of energy supplied by the heater. That's power of the heater. That's rate of energy supplied by the heater is equal to rate of energy absorbed by the water, because the rate of energy supplied by the heater is going to be absorbed by the water, and rate absorbed by the water, and it's not everything that's going to be absorbed. Some are going to be lost. As the rate of its loss. So let's look at scenario one. They said when the water is heated by 25.2 watts. That's the rate of energy supplied by the heater. And the water was flowing at 0.150 kilogram per minute, right? But the rate of water, we are going to use this formula. Q is equal to mc change in theta, right? For work, that's for the quantity of energy of the water. But this is rate, so it's going to be energy over time. So we are going to divide this stuff by time. At the time we are going to divide it, we are going to divide it by 60. Why? Because this we are going to divide the mass by 60 because here it is given as 0.150 kilogram per minute, but it has to be in kilogram per second. So the rate of water will be 0.15 over 60 times specific capacity of water times change in temperature. Change in temperature is 17.4 to 15 point 7.4. That's 17.4 minus 15.2. That will be 2.2. That's 2.2 plus the heat loss. You don't know it, you also have to find that. So here we just have 25.2 watts is equal to 0.15 times 22 divided by 60. That's 0.055 C plus heat loss. That's for that's it. Let's call this equation one. That's for the first scenario. The second scenario, then the heater started supplying the heat at a rate of 37.8 watts. So the water now started flowing at 0.21318 kilogram per minute. As we use MC theta as 0.2318. Then this one will divide by 60 times C, or specific capacity of water, times change in temperature. Since the change in temperature does not change, that will be 2.2. That will be 2.2. That's something 24 minus 14. Okay. Plus the heat loss. That's 37.8 equal to 0.21318 times 2.2 divided by 60. That will be 0.0085 plus heat loss. So let's bring down equation 1, 25.2 watts equal to 0.055 C plus heat loss. So we're going to solve this stuff simultaneously because as you can see it's a simultaneous equation already. So let's call this equation 2. Let's call this equation 2 and let's call this equation 1. Let's subtract equation 1 from equation 2. Minus equation 2 minus equation 1. That's 7.8 minus 25.2. You can just say 37.8 minus 25.2. 37.8 minus 25.2. That will give 12.6. That's 12.6 is equal to 0.0085 minus 0.005. That will give, yeah, so that will give minus 0.0465. Then the heat loss, yeah, so the heat loss will be, when you subtract the heat loss, just get 0. Then our C, oh yeah, so okay, I made a mistake here. This is actually supposed to be 0 point, sorry, here this is actually supposed to be 0.0055. So here to this will also change to 0.0055. 0.0055. Okay. So when you subtract equation 2 minus equation 1, you get 12.6 here. Then 0.0085 minus 0.0055, get 0.003 C. Then it loss HM and HF is 0 because 1 1. So our specific heat capacity will be 12.6 over 0.003. So the specific heat capacity will be 12.6 divided by 0.003. That will be 4,200. So the answer is 4,200. So how do you find the heat loss? We can just put this value of C into any of these equations and we'll get it. So let's put it into equation 1. That's a 25.2 watts is equal to 0.0055 C. Then our C is 4,200 plus heat loss. That will be 25.2 watts is equal to 0.00555 times 4,200. That will be 23.1 plus heat loss. So heat loss, we're going to subtract 23.1 from both sides, 25.2 minus 23.1. That will give you 2.1 watts. So heat loss is 2.1 watts. Heat loss is 2.1 watts. That's how to solve questions like that.